important. With all of that said, it's great pleasure to have the first speaker of this year's member seminar, Professor Zhengwei Liu, Vice President of PIMSA, who is talking about Alterfold topological quantum field theory.
Thank you, Arthur, for the introduction to everything. And well, I'm Zhengwei Liu, and I work on actually several topics, originally on operator algebra and lower dimension topology. My PhD advisor was Wang Juns, and he found the connection between operator algebra and knot theory. And later I get into quantum information at Harvard, and I work with Arthur Jeffrey. And actually at that point, I want to work on quantum field theory, and in particular constructive quantum field theory. But it happened that we found our collaboration first had something to do with condensed matter. And then we found how that's relevant to quantum information. And then we get into quantum information, but never get back to the constructive quantum field theory. So I actually didn't learn much enough at the point. But in this talk, I will show you, okay, everything come together. All story come together. And that's a very exciting point. And this is joint work with our colleagues, Ming Shuang, Yilong Wang, and Jinsong Wu at PIMSA. And also many other people are involved in this project. Essentially, this is a very popular topic. That's the topological quantum field theory that has been developed for more than 40 years. And many people have already won like Fields Medal or Nobel Medal on related topics. So in this talk, I will give you somehow a new feeling. How should we study the topological quantum field theory as a quantum field theory? Even though we say it's a topological quantum field theory, but for some historical reason, it doesn't look like a quantum field theory. It more looks like algebraic topology, and I will explain why. And now we will make it more physical and more accessible. So that will be relevant to condensed matter, quantum information, and constructive quantum field theory in a very, very natural physics way. And also it's relevant to many other mathematical areas. So I hope you will get something from this topic this time. So first, Jones found this very exciting emergence of knots from operator algebra. And this has a lot of other interpretations at the time. Like he found this kind of relation about the braiding, and we can switch the positive braid and negative braid and up to some identity. And this is the Hecke algebra relation. And then he proved that this relation verified the Yang-Baxter equation. So that gives you a braid group representation. But there's an amazing fact that you can take the trace, the Markov trace of this knot, and then show you, okay, this give you the red massive move of 1, 2, 3. So you get a knot invariant. So where is the trace from? It really comes from operator algebra, from a fact that the infinite dimensional operator algebra has a normalized trace, and such that the infinite dimensional Hilbert space will have a renormalized dimension, which is no longer infinity. So it will become a finite number. Now we call that a quantum dimension. So that has a very natural interpretation for the quantum dimension. Now from that, later people found that concept in representation theory and also introduced the quantum dimension on representation like for quantum groups with some analog, even though it's no longer renormalized dimension, but there are some counterpart of that. So from those representation, we can get knot invariant and not just for the Jones polynomial. That series for SU2. So people can generalize that to other quantum groups and get interesting quantum group representations and the knot and link invariant, like the Helmholtz-PT polynomial for SUN and the Kaufman polynomial for the type DCD quantum groups. And that also works for other Lie groups. And actually, there are even exotic examples beyond quantum groups, which could give interesting invariants. And then it's a central question, okay, what's the meaning of the Jones polynomial in physics? And Atiyah wants to find a good interpretation, in particular in quantum field theory. And here, the story is that later Witten found this very nice topological quantum field theory, and such that you can take a passive integral along the link or not in the 3 manifolds with some gauge group, that's the Lie group. And then by the passive integral, you can find the reasonable invariant. And since the local term is given by the Chen-Simon form, which is independent of the matrix, so the integration becomes topological. It's irrelevant to the matrix. In that way, you can get a topological invariant. So in that sense, the topological invariant of the 3 manifold together with the link inside will be the partition function in the quantum field theory. And that's topological invariant because the local term the chain segment is irrelevant to the matrix. However, the path integral is a very nice physics concept, but usually it's not well defined mathematically. And this is also the case because the space of all passes is a huge infinite dimensional space, and there's no reasonable measure so that you can define the integration. But at that point, RTS said, okay, we don't get into that tricky point. We can formulate this invariant in another way as a mathematical version of TQFT. And what's that? It's actually just telling you if you have an invariant of a manifold, what can you learn from that? Say if you have a 3-manifold invariant, okay, then what do you learn from that? You can cut the 3-manifold, and you can take a manifold with boundary. And then if you have 2 manifolds with a common boundary but opposite orientation, you can glue them together, and then you get back to the invariant of 3-manifold. That's a scalar. So the 3-manifold invariant gives you an inner product of the vector space for a given boundary. So then he axiomatized that given a 2-manifold boundary, okay, you have a vector space. And given a cobordism, you will have a linear transformation acting on the vector space. Okay. And if you have a manifold without boundary, that will be scalar. And that's the axiomatization of RTS TQFT. So essentially just say what you learn from an invariant of a topological invariant of a manifold. And you can learn those kind of cobordism as linear transformations. And then the question is, okay, then how do we find the examples? Like how do we find the Jones polynomial? And then Rashid and TQFT, they gave a nice mathematical realization of Wheaton's theory. So okay, if the theory really works, then we can use the links to do some surgery theory, and such that we can get the invariance of 3 manifolds from the invariance of links and knots. And those will satisfy actual condition. And those actual conditions are verified for representations of quantum groups. So in that sense, we do get the very nice Wheaton, Rashid and TQFT. But essentially, they're not invariant, not really quantum field theory. Okay. Even though the original motivation is in quantum field theory. And then at that point, Greenfield, Jones, and Wheaton, they all win the Fields Medal in 1990s in Kyoto. Yeah, did I write something wrong? Oh, Tokyo, sorry. Yeah.
It's a metal, even though it's made of metal.
Thank you. So since then, the 2 + 1 dimensional theory is really well studied. And there are a lot of interesting examples from representation theory of like groups, quantum groups, vertex operator algebra, subfactors, and many other literatures, conformal field theory. It's so rich, and there is a main reason because we have studied group theory for 100 years. And we have a lot of pre-knowledge about that. And also we know the 3-manifold very well. We know the surgery theory. And later people can construct more and more invariants from the surgery theory, like Rashid and 12 type, or the general result about 12 Vero and Barrett Westbury from just the fusion category, like a tensor category, given by like representations of a Hopf algebra, which doesn't have to be a quantum group. But how do we generalize this to higher dimension? It's not really known, since we don't have higher dimensional Lie groups. Or many other things are lack of mathematical definition in higher dimensions. You can imagine how they look like, but we don't really have the formal mathematical foundation for the theory. In particular, we want to understand the higher dimensional structure of quantum field theory. And in that direction, people try to understand, okay, if we have an n-dimensional topological quantum field theory, or just invariance of n-manifold, what do we learn from that? Not just the vector space for the codimensional 1 manifold. Okay, so for each codimension 1 boundary, you have a vector space. Then they say, okay, maybe we just cut it again. We have codimension 2, codimension 3, and so on. And until we to the end, we get a point. And then we should have interpretation of all those codimensions. And the answer is that will be an N category. So that's a higher categorical structure behind the TQFT. And that's the cobordism hypothesis. And it has been proved by Hopkins and Lurie in dimension 2, and by Lurie in 2009 for all dimensions. So that one can study the TQFT from the view of algebraic topology, a kind of a quantum version of algebraic topology. But still, the problem is following. This gives you interpretation how it should look like, but it doesn't tell where are they from. Such how to construct such kind of example with a huge amount of axioms. For 2+1 dimensional case, we can construct examples from like representations of group theory of quantum groups. Another thing is that we can solve this in abstract way, saying, okay, we can try to construct the fusion category. That's a categorification of fusion ring. And the fusion ring is just something combinatorial. It's easy to solve by computer. And the categorification is just solving the Pantagruel equation for that. It's not easy, but for small examples, it's doable by hand and by computer. And so far, somehow I think so far the people have tried enough such that we exhaust all the possibilities that can be done by computer. So somehow we found all kinds of examples there. And if we want to construct new example, we have to get a better understanding of the mathematics rather than just solving polynomial equations. So that's kind of the current status. But for higher dimensional case, the number of equations grows really exponentially, and solving just the number grows exponentially. And solving the polynomial equation using like Lagrange basis grows double exponentially. So that will be triple exponentially. There's just no hope. Okay. So that will be just too complicated to solve the equations directly in the brute force way. And there's another approach that's somehow more physical to look at the quantum field theory. So if it's some quantum field theory, at least we should get a Hamiltonian and a Hilbert space. And in that sense, for 2+1 case, people have tried to construct a two-dimensional lattice model with a Hamiltonian and read the TQFT from its ground state. And that corresponds to a theory at 0 temperature. And the general idea is that if we have a Hamiltonian on 2D lattice model, we can look at the ground state on the local piece. And then we can glue the ground state together. If the Hamiltonian is gapped, then we'll glue the ground state. The energy is still very low, so it's still gapped. So you can keep that. You can glue those local pieces together. You can glue the local piece from the local disk to a 2 manifold, and that will give you a 2D theory. And then for some magic region, the 2D theory is actually the boundary theory of 2+1 TQFT. And that's actually the point we explained in our recent work on the Alterfold TQFT. How do you go from a 2-dimensional theory to the higher dimensional TQFT such that the original theory is on the boundary? And that works in all dimensions.
So for someone who is not familiar with these words, what's gapped mean?
So Hamiltonian first is a self-adjoint operator. It's easy to understand. And then for the operator, you can look at the spectrum. Say the lowest one is 0. Okay, and the eigenvector for that is called ground state. And then for the next eigenvalue, say maybe it's 1 or something different. And then this difference is called the gap. And what's the meaning of the gap Hamiltonian? So we are not only looking at a Hamiltonian on a single lattice, but we are taking a limit of lattice, like large scale limit or containment limit. We want to show this gap is preserved when we take the limit. So that's called a gap Hamiltonian. Okay. So actually there are phenomena that the Hamiltonian is gapless. That means when we take the limit, the gap will disappear. And that's another phenomenon. But actually in our theory, it will involve both cases. And why they are interested in that, actually, it's not really originally from TQFT. It's from the called topological orders. Just people, when they study the ground state of a gap Hamiltonian, they expect that the symmetry of the ground state are all group-like. And that's the original theory of Landau for phase transition. Just they describe the phase transition by looking at the symmetry breaking of group symmetries. And then the appearance of quantum Hall effect gave a counterexample. There are symmetries beyond the group symmetry. But still, when we look at the ground state, it has degeneracy. And the Kitaev gave a very nice example that looks more easier, more accessible on the torus, and give the same phenomenon. So that's a non-trivial topological order. And then level Wien showed that from any tensor category, you can actually construct such example with non-trivial topological order. And that gives the also connection to the TQFT. And in principle, if you look at the ground state, previously people just say, okay, if we have a ground state and how it should look like, how do we describe the symmetry? Now in this new type of ground state, we should look at the symmetry using TQFT. Local theory is captured by the N category, and the global theory is captured by the topological quantum field theory. And this is Kitab's story code. So we take a square lattice, and on each edge, we have a qubit. And the qubit is just a vector state in a 2-dimensional Hilbert space, the spin up, spin down. And then we can take the action of Pauli matrices. So at each vertex, we take the neighborhood action on the 4 qubits by Pauli Z. And then for each plaque height, we take the neighborhood in action by Pauli X. Then you can check all those operators, local operators, they can muse with each other. Okay. And they are operator with all the Z2, so they have eigenvalue plus minus 1. And then you can look at the ground state, or the stabilized state that's preserved by all those operators. Since they all commute, so essentially we are looking at the common eigenvector with eigenvalue 1 for all those operators. And then the interesting part is, if you look at all those operators, and the stabilized state is 4-dimensional. And in quantum information, people consider that as 2 logical qubits. On the torus, actually, from the homology theory, we have 2 different cycles. And that really corresponds to the 2 generator of the 2 logical qubits. So that gives a topological interpretation of those logical qubits in quantum information. And that has been widely studied in fault-tolerant quantum computing, since the topological behavior is very fault-tolerant. You can easily detect the noise and make error correction for that. So that's kind of the important idea to use this global topological data to encode the logical qubits. Z of
this product you're taking over Z and X. What is Z and X again?
Z is Pauli Z on the neighborhood. Pauli Z is diagonal matrix 1 minus 1. And Pauli X is just it change 0 to 1, 1 to 0 to switch. Yeah, Pauli matrices. So essentially, when we have the ground non-degeneracy of the ground state, it's really relevant to the topological structure. So if we put it on the sphere, then the ground state will be 1-dimensional. If we put it on 2 torus, then we have an additional ground state degeneracy corresponding to the homology. And for the lattice, actually, we can change the shape a little bit. Okay, we say at each edge, we have a qubit. Now we change the edge to the small disk, so that we can somehow, you can think about, we can fill the qubit in the small disk. Okay, we just change the shape of lattice. Now it becomes a new lattice, and the edge go in the 45-degree direction. And then the original operator, like both vertex operator and the plaquette operator, becomes plaquette operator in this case. So somehow in this refined lattice, the symmetry becomes better. So you can just look at the plaquette operator. And actually, this is a general phenomenon. We can always do this kind of very nice translation. And there's another interesting phenomenon from this translation. If we look at the previous lattice, if you look at the corresponding representation category theory, we can read out the Z2 category, representation of Z2. And if we use this lattice, then we can actually get additional information. We get the so-called Ising category. So it has an additional representation tau, whose dimension is square root of 2, and tau square is sum of Z2. So that's the Ising type of category, just by changing the shape of lattice. And this is a very nice changing. And later, actually, we will use this idea in 3 dimensions. So you can do the same thing for the 3-dimensional case. You also have the vertex operator. Then you will have 6 edge nearby a vertex. And for the plaquette operator, you still have this square-like plaquette. But then in the 3-dimensional case, it's no longer the 45-degree. It will be in the direction normal to the vector 1, 1, 1 rather than 1, 1. It's 3-dimensional case. And then you have 4 families of parallel faces. You can also change that kind of symmetry. And then the fascinating point is that then if you start with the Z2 symmetry in the 3D case, that will be the 3-dimensional cohomology, but with trivial coboundary. And then extend that to the 3D Ising model with 3D categorical symmetry. Okay. So in this way, we can find a very new example. And actually, this method really works in higher dimensions. Now, for topological orders, people try to understand the phenomenon in higher dimensions. And like Xiaogang Wen, Liang Kong, and Hao Zheng is faculty at BIMSA, and many others, and they have investigated the general theory of n-dimensional topological orders. That's the study of those kind of ground states and the non-trivial topological symmetry behind the ground state through the n categories, like in the cobordism hypothesis. We study the local property in the local n disk. and that's captured by the N category. And actually, to construct TQFT, there are some additional conditions beyond the category. The category really, the N category really looks is really cubic like. We can have like the 0 morphism at point, and 1 morphism is mapped from point to point in the first direction, and the 2 morphism is from line to line in the second direction, and the face to face in the third direction. It's really cubic. But to make it topological, we have to curve all the cubes, and that's required in the as the so-called spherical condition for the lower dimensional case. So for higher dimensional cases, it's actually similar. To really construct the TQFT, we need this spherical condition additional to the monoidal N category. But before, actually, there's even no definition for the spherical N category. There are a lot of attempts to do, but so far no formal definition yet. And actually, in our framework, we will come up with a formal definition. It's not in that favor, but it's an equivalent definition. And we want to construct the topological order and the TQFT from such kind of data, N category data. And there are examples like from the group cohomology, and there are higher dimensional examples. But from there, when you look at the invariant, you only get the invariant from the group cohomology. It's a classical invariant. And we have understand that very well. It doesn't give anything more powerful. So it's actually lack of resource to construct non-trivial examples, like non-group-like examples. And in particular, like higher analog of quantum groups. Yeah. And actually, what's the meaning of higher analog? Here, I give a quick comment. From our point of view now, the operator algebra is really a one-dimensional algebra, since you only have multiplication in one direction. And the quantum group, or like half algebra, is two-dimensional. You have multiplication in two different directions. And when you go to higher dimension, you have more and more directions for the multiplications. And then indeed, we will have such kind of structures. So what should we expect from this topological order? First, we want to have a good Hamiltonian lattice model. And for the local N disk, it's described by the N category. And the ground state should give us a topological order. And the ground state should be independent of the shape of lattice, but only depends on the underlying N manifolds. So it's topological. And further, the symmetry is described, the global symmetry is described by the TQFT. Okay. And in particular, we expect that the invariant of the N+1 manifold should be non-trivial. Now here is our main theorem. We don't really construct such a kind of TQFT from the N category, because that's also very difficult. Instead, we will show the N category will be an emerging symmetry. So previously it's given by axioms. So we take that for free. Now we don't take that for free. We say, okay, there are even more fundamental structures in the physics literature. And when we construct those more fundamental structures, the higher category will emerge. It's not an input. So we constructed the N+1 TQFT with all kinds of expected properties from a linear functional on the N-dimensional lattice model. And this linear function has three properties. First one is a homomorphic invariance. And second one is crucial, that's reflection positivity. And third one is a mathematical condition. There's some kind of finiteness condition corresponding to the entanglement rank. And the first one is a common condition people take. Homotopy invariance is to ensure the theory is topological. So what's the meaning of that? So for the He-type honeycomb lattice, we see all the local placket operators just look the same. So homomorphism on lattice just means you take a automorphism of lattice, like you can shift the lattice, you can rotate the lattice by 90 degrees. But you will see the local operator is not changed. So that's the homomorphic invariance property. So it's always the case, since when we consider the local interaction should only be relevant to the local shape of those particles. It's irrelevant where you put it. So that's the meaning of the homomorphic invariance. And this is stronger since we are looking at the topological theory. This homomorphic invariance is independent of the matrix. That's why it becomes a topological theory. So you can look at the big placket. You have placket operator, it's 4 poly Z. You can also have a small placket, it's also 4 poly Z. It's irrelevant of the size. So if it is relevant to the set, then the theory is no longer topological. Instead, it will be geometric. Okay. But here we are focusing on the topological theory. So we say, okay, the local operator, the Hamiltonian, only depends on the shape, but not the matrix. Okay. So this is kind of a matrix analog in the Chen-Simons theory. That the differential form is irrelevant of the matrix. Here, the local Hamiltonian is irrelevant of the matrix. And the second condition is really crucial. That's the reflection positivity condition. And in constructive quantum field theory, that's a key point. Related n-dimensional lattice model of Euclidean theory for statistical physics, and then the n-dimensional quantum field theory for Minkowski space. So you can take the weak rotation and change one space direction to the time direction. And how do you do that? On the space direction, you are considering a certain kind of passive integral. And when you take the rotation, you need to have a linear functional such that this linear functional is the result of the inner product for a passive integral. And then that condition is the reflection positivity condition. And actually, Gleeman and Jaffe, they prove that this is somehow the necessary and sufficient condition based on certain regular mathematical condition, but the physical condition is just that. That means this functional integral with reflection positivity is the right mathematical formulation to define passive integral rigorously. Okay. So it's kind of a measure. So if you look at back to the very classical functional analysis, you probably know this result that any positive measure, regular measure, is given by the positive linear functional. That's the Riesz representation theory. Here is a higher analog. Here you see if you have a reasonable measure for the path space, okay, then the linear functional will have reflection positivity rather than just positivity. So this is really play the role of the path integral, and that will give you the quantum field theory. Now we have that condition. And the third one is just saying, okay, for the n category, all the equivalence class of K morphism are just finitely many. And that's really a technical condition since we want to make sure the partition function as a state sum is a finite sum. So if we allow a convergence of infinite sum, it's fine if it's infinite. And actually in the last week in Sergei Gukov's talk, they are talking about infinite dimensional TQFT and looking at the formal power series and the convergence radius of certain complex functions, analytic functions. Okay. So the first two are really crucial. The first condition make it topological, and the second condition make it quantum field theory. So these two together make it topological quantum field theory, and the third one make the partition mathematically well defined. And from this TQFT, we can recover the original linear functional inside the TQFT as the ground state of a gap Hamiltonian. So this gives interpretation that the physical intuition in that sense is correct. So the TQFT somehow comes from certain kind of ground state of Hamiltonian. Yeah. But previously, people construct the Hamiltonian using the n category and then derive the data of the n category and TQFT. So here we resolve the problem. We don't take that as input. We take the small fundamental property, the linear function. And then we can actually derive the n category from that, both the examples and the definition of spherical n category. Now, later we will see example, how do we find such kind of function with reflection positivity. But recently we found there could be even a machine to construct such function of reflection positivity. So to me, when I studied like operator algebra, subfactor theory, and all those relevant topics, the proof of reflection positivity is always the most difficult one. Not even one of the most, it's just the most difficult one. It's very hard to prove. But then we found a very nice method from the early work of Gleeman Jaffe and my joint work with Arthur in 2015. There is a very nice proof of reflection positivity on a single lattice. And here we need to generalize the proof for all kinds of lattice for given boundary. That means for different lattice, we have the wave function for different lattice. And we need to take the superposition of that. Since in TQFT, we only fix boundary, we consider all possible bulk lattice. And then we take superposition, we want to prove the inner product is positive on that. So we have to improve the previous method in constructive quantum field theory, but it works. And this gives a very nice, very powerful proof of reflection positivity of Hamiltonian with very simple assumption. Just saying the Hamiltonian is given by the sum of Plackett operators. And each Plackett operator comes from matrix product operator. And in certain cases, it has a geometric meaning that corresponds to the connection. So we just come back to the theory, like latest version of the Chen-Simons theory. We use the connection to build up the operator, and the reflection positivity always holds. So we always have quantum field theory. So this is really fascinating that this ensures the reflection positivity. And like for Kitab's case, okay, it verified this condition. So we no longer need to check reflection positivity or prove that. It's just there. So this is a very powerful result showing the reflection positivity is a universal phenomenon and only requires some very reasonable minor assumptions on the Hamiltonian. And this is not used before. And actually, to me, it was very surprising since the theory of Glim-Jaffe on constructive quantum field theory was kind of 1970s. And it's really distant from the topological quantum field theory for a long time. People try to understand the connection, but just it seems not that relevant. Even for myself, when I look at two topics, I'm quite confused. Since in constructive quantum field theory, we go from an n-dimensional lattice model to an n-dimensional topological quantum field theory, not an n+1 dimensional. I just don't understand where is the +1 coming from. But here, actually, we will have a better interpretation. Where is the +1? It's from this Hamiltonian H. T is on the n-dimensional lattice model, but we have the action of Hamiltonian. And when we take the action of e to the minus beta h, this will give you the extra dimension. That's the bulk dimension for the TQFT. And the previous TQFT just studied the ground state. That means the temperature is 0. And then this beta, the inverse temperature will be infinity. So we will only see the theory for the ground state. But now in this proof, it's true for all temperatures. So that means this will give a foundation to have the topological quantum field theory for any temperature. Previously, even by definition, topological quantum field theory is a theory for 0 temperature, even though we talk about the excitations. But it's kind of a paradox. How do we get excitation from 0 temperature theory? And here, actually, we can get the theory for general temperature. And then we can even have a theory for phase transition when we change the temperature. So this will make up the building block in the physics literature. Now we have temperature. And actually beyond that, we even have time. We have the time translation and given by the transfer matrix. And the previous TQFT will be a theory that's invariant under the time translation. And you can also interpret that as the theory at time equals to infinity. Okay. So the previous TQFT, like RTS type TQFT, is the limit of this small general TQFT at 0 temperature and infinity time. Here, actually, even though we are talking about n-dimensional lattice model, but the mathematical definition, the formal definition is really delicate. It takes me quite a long time to give the formal definition using a stratified piecewise linear manifold with certain regular conditions. But we will skip that part. That's really the highly non-trivial part. Now let's talk about the example. Just as we mentioned for the 2-dimensional case, we can go from Kitab's Tori code and then change lattice shape. We get to the eigensymmetry. This is just the same for the 3-dimensional case, even higher dimensional case. And then we can read out the function. And then the data tell us we can construct this kind of function, this linear functional, with the 3 properties. And the function looks actually very simple. Just in the 3-dimensional case, in the 3-sphere S3, we want to define a function. And then we have data inside. The data will be closed surfaces inside the 3-sphere. Okay. For the 2D case, we have those like closed curves in the 2-sphere or like torus or 2D surfaces. And each closed circle in 2D case corresponds to the value of the quantum dimension, that's square root of 2. And here in the 3D case, the value of the 2-sphere is still square root of 2. So that it's square. Okay, its dimension square will be 2, and that will decompose as the Z2 symmetry, but the 3-dimensional Z2 symmetry. But in the 3-dimensional case, we not only have the sphere, we also have torus, a homogeneous surface. And then the value will detect the Euler number. Okay. So for each surface, the actual value is 2 to the 1 minus the Euler number over 4. So that's the definition of a partition function. So we can just derive this function from the lattice model. And there are other ways to understand this function. Actually, the lattice model is not the original way we get this example. We get this one from very complicated computation. But after we understand that, we say, okay, there's a very simple way to get to this example. We can show, obviously, this function is isotopic inverse. And it's not that obvious. This function has reflection positivity. But since this comes from this lattice model with a Hamiltonian, and then by the previous theorem, this reflection positivity just holds. And then for the finiteness, it's actually not that obvious. If we allow the surfaces in the 3 sphere without intersection, the finiteness fails. It's not true. Only when we allow intersecting surfaces, we will have the finiteness. Okay. But that's another mathematical technical part. And after we have that, we will have this 3-dimensional function and the 3 plus 1 TQFT. And actually, we can read out the classical 3D Ising model from this model. Okay. So
Can I
then
ask you a question real quick?
Yeah.
This is my cell phone is a sphere.
Mhm.
If I take the top surface of it, with respect to what is, am I taking the mirror?
The mirror?
Yeah.
Ah.
So this top surface of my cell phone,
Yes.
you're saying under the reflection, that Z is positive for this
So
top
for the
surface.
surface, it's S3, and then you cut that
Cut in the
by the
middle?
equator. Yes, cut in the middle.
Uh-huh.
And then you reflect the left side to the right side.
Okay.
Yeah. And on
And
left
then
side, you
calculate
have
the-
some surface with boundary on the mirror.
Okay.
And when you take the mirror image, when you glue them, you get the closed surfaces. And that gives you the scalar, the inner product.
Okay.
And we need to prove that inner product is positive, semi-definite.
Thanks. Uh-huh.
So then we can read out the 3 category data just from the local disk D3. And it has a 0 morphism corresponding to the background, and 3 1 morphisms of Ising type. Tau square is 1 plus G, and G is the generator of Z2. It also has a diagrammatic representation of those. And actually, when we say we are writing the morphisms, it's really a higher representation theory. We are doing the idempotent completion of the algebra. So looking at the irreducible representations of the higher algebra, and also the interaction between representations. Here, once we have the 1 morphism, we can look at the modules between 1 morphism. That will be 2 morphisms, like this. Just on the simplicial complex, look, if we take the boundary, we have those modules corresponding to the 0 point or 1 point, 2 points on the edge. And when we have all the labels on the boundary, we can fill the possible shape inside the 2 cell. And that will be the 2 morphisms. And there are only finitely many. And actually, we can even draw not just the triangle, we can draw even polygon. And it's also finite. And then the 3 simplex. When we draw all this kind of boundary on the face, and then we can see, okay, what we can fill in the bulk. And we look at all the possibilities. And there are many, but still finitely many. Okay. Yeah, really a lot. And after we have the 3 simplex, then what do? We glue all the 3 simplex together into a 4 simplex. And then that will be some graph on the 3 sphere. That's the boundary of the 4 simplex. And then you get a scalar. And that's a higher analog of the quantum 6G symbol. Now we have quantum 20G symbol. And I think in the previous literature, I found the largest number is 15G symbol. And this will be a 20G symbol. And then you see, even draw the label for the 20G. It's a big table. But the F symbol is just the last row, just those numbers. And we should say we'd be able to say something about numbers. Okay. And they should verify the Rett equation. In the lower dimensional case, that's a famous pentagon equation. And that corresponds to the so-called the 3 to 2 puncher move. Now in the 1 dimensional higher, we will have the 3 to 3, 4 to 1, 5 to 1 puncher moves. And there are about more than 500 equations. And we check that, and that's true. So theoretically, we know this has to be true. But numerically, we really want to check that. Both check the computation of data and check whether our theory is correct. Since this is so far the only example we can check all those kind of equation and theory in a non-trivial way, and eventually it works. Thank you for your attention.
Questions?
What's a plaquette operator that you mentioned in one of the slides?
The plaquette operator, you mean the
Yeah.
2D case?
Yeah.
Just in a 2D lattice, for each plaquette, the square, you have the action of the 4 poly X on the 4 qubits, on 4 edges. And that's the plaquette operator.
Okay, so is a sum of the operators on the
No, just a
vertices?
single, it's a tensor product of the 4 poly operator.
Oh, okay.
And that's a single plaquette operator. And then you need to take the sum of all plaquette operators, and that's the Hamiltonian.
Oh, okay. I see. Thank you.
Thanks for the talk. So I want to ask like 2 questions. Maybe they are both vague, but is there a spin story to this? Spin version of this story?
Of which one?
Like a spin TQFT? Is there a version of that for that?
Oh, spin version. That's a very good question.
Yeah.
I would say the answer is yes, but it's non-trivial. Since when I take the definition, it's really delicate. I remove the possibility of the spin structure. When I assume this is homotopy invariance, I really eliminate the possibility of the spin structure. But in the definition, actually, I see the construction doesn't really require such a strong condition, the construction of TQFT. We can have a spin structure, just the 2-pi rotation give you plus minus sign. That's really possible. But why I didn't take that as in the definition? First, that will make the notation extremely complicated. It takes me already 4 months to just simplify the notation. So I try to take the most simple case because it's really already very complicated. And also for the spin structure, so far in the higher dimensional case, I don't see a non-trivial example, even though I believe there must be a lot of examples with the spin structure. So without the example, it's hard for me to say, okay, what should be the right definition? But since in the 2+1 theory, there are interesting spin structures. So that indeed happened. And actually not just the spin structure, we can even release that further. There are further additional structure. Say we take homotopy invariance, namely we can have the translation and the rotations. We can even eliminate all the symmetry of the rotations. And that gives even more interesting structure. And also we can eliminate the symmetry of scalings. And so that is more rigid. And just then we are moving from topology to geometry, just step by step. Yeah.
That sounds a lot like fractons.
Yes, indeed, the spin structure should be the next one to study. Yes.
Okay. And the second question, maybe I'm able to. So it's more of a more specific question. Maybe you can go back to the slide with the one of the theorems that you had. It's the one about the reflection positive. Yeah, that one. So here you're assuming that your Hamiltonian is just a bunch of plaquette operators. But what happens if I have interactions between plaquettes?
It's also true.
It's
we can also have link operators. Yeah, and actually there's a very nice example. That's Kitaev's honeycomb lattice model that has both plaquette and the link operator, and the local operator do not commute. This theory also works.
Nice.
Yeah, and actually in that case, the honeycomb lattice, we can also read out a tensor category from that. It's not Ising, even though he constructed from Ising. Yeah, the answer is E6. That's a very surprising point. There are additional hidden symmetry from non-commuting local operators.
Okay, thank you.
I find it hard to believe you don't have more questions. There is one question. What does the topological order mean here?
Okay. In similar
someone is
rotation
answering.
and grace, preserved shape doesn't work. It's not orthogonal. Okay, I'll answer the first one. topological order means somehow you look at the ground state, they are really different. Actually, there's no formal definition of topological order. There are different definitions, and they have overlap. And one of them is the following: that if you take the TQFT and then you look at the space, the given boundary, it comes from the gap Hamiltonian, the ground state. That's by definition topological order. Another one is the following: you have this state is usually highly entangled. Another one is that you cannot take a finite depth circuit from the product state to this kind of topological state. So that has non-trivial phase, non-trivial order, and that's another thing called topological order. But actually, this is still not a happy definition comparing to the order, the concept of the order in condensed matter physics. And I think I will give you a much happier answer when we write down the next paper. We'll explain what should be the right meaning of topological order, which has the next counterpart in the classical condensed matter. Yeah. And for the three-dimensional case, the second question, rotation of the grid that preserves shape doesn't work. It seems also, yeah.
We got it.
It's good. And well, here when we look at the lattice, we only take lattice of like the square shape lattice, but actually the lattice could be any shape you want. It could even have no symmetry. We really take all possible shapes. Just you only have the local shape. Like you can have for the square, you have the forward vertex in local shape. You can have a travel vertex or other type, just fix the local shape. How you glue the local shape in the general, it doesn't matter. So theory really talks about all possible shapes. And then we talk about symmetry. So we just take any lattice and take all possible automorphisms on the lattice, and such that the function is preserved and this kind of action. Yeah.
More questions? So what do you mean exactly by group-like n category?
Oh, group cohomology. Yes. Yes. Another definition is if all the morphisms are invertible, so all dimensions just one, then that's group-like.
More questions? So can I ask you some simple questions? So I'm algebraic geometer. I don't do this. Let's say I give you a cubic lattice. You're saying that for the vertices, I put the vector spaces. For every vertex around it, I can construct a placket operator, add them all, put it in this formula. As long as I can make sure that any way I cut this cube in any of the planes, this symmetry and positivity is satisfied, I can think of this lattice with the tensor product of all the vector spaces at the vertices as being a boundary of a topological QFT.
Yes.
Of a 3+1 TQFT.
Yes. I can give an even better answer.
Okay.
In algebraic geometry, okay, it's hard to verify positivity. Since that's essentially saying the polynomial is positive. So that will be sum of squares. But this theory, the construction of the TQFT, if you look at our construction carefully, somehow it's irrelevant to the vector space. You can really generalize the concept even to homology and cohomology.
Right.
What we really need is a dual structure in the construction, not even just the vector space. It's due to vector space. That's what we really need. So I think that will be more appropriate to the algebraic geometry concepts.
Okay. Can I ask you an evil question?
Yeah.
Okay. What does this say about Poincare conjecture in dimension 4?
I didn't talk about that in this talk. It's all the theory, once we say reflection, yes, once we say reflection positivity, the theory is semi-simple. And there is a general result saying all kinds of semi-simple TQFT will not detect the exotic structure of false spheres. So in that sense, it will not solve the four-dimensional Poincare conjecture. And actually, I even have a more stronger version. Somehow, many kinds of TQFT won't solve that conjecture. But by proving that stronger version, I can see what is really needed to solve the conjecture. And our construction actually will give a somehow clue, I would say clue, to get such example, but it's a long way to really get to that point.
Okay, any more questions? If not, let's thank Zhengwei again.